Hey, hi everybody. Thank you for, okay, let's figure this out. We good? Okay, we should be good now. Hi everyone, once again, thank you for the introduction. We'll be starting, and before we start, I want to ask you two questions. How many of you are familiar with the field of causality? So it's around 50%. Okay. How many of you are familiar with deep learning? Deep learning, like most of you? Okay. Perfect. Good to go. How many of you are familiar with directed acyclic graphs? Okay. Okay. So we will do it for both groups, for those familiar and not familiar. Great. Let's start with an example. So imagine you have a friend. She's a researcher in some field, whatever the field is. And she comes up with an idea that addresses a long-standing problem in her research area. Okay, some novel solution to a problem that people were trying to solve for a long time. And she publishes a paper. Now, let's call her Jane. You have another friend whose name is Jake. And Jake reads Jane's paper. He publishes another paper that builds on top of her discovery and adds a couple of ideas. But they are not that novel. They are not that revolutionary as her ideas are. And they do it in a very short time period. Now, 12 months passes, and Jane's paper gets 573 citations. But Jake's paper gets 977 citations. So it's almost twice more. Now, there might be many reasons for this. So maybe they have different affiliations, and Jake's affiliation is better, more popular. Maybe they publish in different journals. Maybe they have different writing styles, and Jake's writing style was more compelling to the readers, or maybe easier to understand. And there might be more factors like this. But one factor, and there's a research like this, a potential factor can be Jane's gender. So there's a research that is showing that papers that have authors who are easily identified as female by their names, for instance, are cited less frequently there than papers by the male counterparts. So now, sometimes we might be interested in answering a question if gender could be a factor here. So was it about Jane's work, something like a journal, something like an affiliation, or maybe about her gender? Or, to be precise, the perceived gender, right? Her perceived gender, how people perceived her gender. So we can ask a question like this. Holding everything else constant, would Jane have been cited more often had she been perceived as being male? And this question is a counterfactual question. And we ask those questions and similar questions in the field that is called counterfactual fairness. And this is one type of questions that the intersection of causality and NLP is trying to tackle. There are more questions. We'll see other possible questions in a second. And before we go to the meat of this presentation, let me tell you 5 words about myself. My name is Aleksander Molak. I love traveling with my wife, running, and I enjoy good vegan food. For the last 6 years, I was helping Fortune 100, 500, and 5,000 companies building machine learning systems. And I'm currently finishing my book on causality and machine learning. So if this is something that is interesting to you, you can scan this QR code and get to a page and subscribe for the updates on the book and also for a newsletter with curated causality-related content. Okay, so how are we going to structure the presentation today? So we'll start with an overview, what is causality. For around 50% of you, this might be a little bit boring, but I'll be asking questions, so maybe you will have an opportunity to have some fun. Then we'll talk about LLMs and causality. What's the connection? And we'll start talking about the large language models that are popular today and give an overview of the intersection of how they work and how causal they might be. Then we'll talk about two streams of causal NLP. Then we'll introduce the architecture we'll work today with. It's called Causal BERT. And finally, we'll have some time for questions. Okay, so what is causality? This is the definition that Wikipedia gives for causality as understood in physics. Causality is the relationship between causes and effects. What are your thoughts about this definition? Is it a good definition? I'm pretty sure you have opinions.
It's a bit large.
Bit?
It's a bit large.
Bit large.
Yeah.
So not specific?
Yeah.
That's what you mean?
Yeah.
Mm-hmm. Okay. Yes?
Can be, the relationship may not be true.
The relationship may not be true. Mm-hmm. So what you're saying is that this definition does not say anything important about the relationship itself?
Yeah, we are testing the relationship maybe, but we don't know yet.
Mm-hmm. Okay. Great, thank you. Any other voices? Yes, go on.
It really sets it apart from a correlation.
Does it really set it apart from the correlation? Very good question.
Doesn't say anything about direction, because I think intuitively one would assume like causation leads to the effect and not the effect to the cause.
Mm-hmm. So what you say is that this definition is not very precise when it comes to the direction of this relationship. Mm-hmm.
Is it circular? Because causality and causes are the same.
It's circular. I also think so. So circular in definitions means that it defines the term causality using the term cause. That likely is defined by using the term causality. So it's self-referential, yes?
More steps to a diagram, right? You would have a treatment and you could look at that and then also have several factors that are like like some other, not counterfactuals, but confounders
Mm-hmm.
and so on, and you could look at that and that would make a difference and make it more specific.
Mm-hmm. So what you're saying is that it only talks about causes and effects, but doesn't talk about other elements that could be involved in a system and could modify this relationship. Is that correct? Great. Thank you. These are all great. These are all great, great ideas and great comments. What do you think what causality is? And this can be about intuitions. Don't worry if it's correct or not. It's more about understanding what are your intuitions. So like around 50% of you said that you have some experience with causality, so some understanding. So let's get some intuitions. Maybe from the people who rose their hands or the other half. Okay, I see you want to say something. Don't be shy. No? No, not really. Okay. Okay, anyone? Yes?
Maybe to a certain extent quantifying the effect that a cause has on something else, and to the other extent also learning about these relationships, so discovering the structures,
Mm-hmm.
even coming up with ideas of what could influence what.
So you said it's about quantifying. So causality is about quantifying how one element influences other element. That's what you're saying?
On the one hand,
On the one hand, okay.
and then on the other hand, maybe even coming up
and coming up with ideas what could have influence on something else. So that would be discovering causal mechanisms. And the first part you mentioned would be about just quantifying the strength, yes, strength of effect. Okay, that's great. Do we have any more voices here or here? Yes?
Maybe to find out the real root cause of an effect or phenomenon.
Finding the real root cause of the effect. Yeah, that's very good. How could we do it? How could we operationalize those ideas? Both the three ideas that we heard about. How could we easily define it? An experiment could help us. So experiment. So what would be an experiment, for instance? An A/B test.
Giving someone a blue website and an orange website and see, and really only tweaking that one parameter.
So intervening on one parameter in the system and looking what is changing in the system, right? Great, thank you. That's a great intuition, and this is very similar to the definition of causality that we will use today as our main definition that comes from Judea Pearl. And this definition says, it's a very simple definition, so maybe even embarrassingly simple, but I think it's beautiful because of its simplicity. And it states A is a cause of B if B listens to A. So this is what you said about A/B tests. We change something. We intervene on the system. It's a targeted intervention, so we only intervene on one aspect of the system, and we observe how other elements in the system, in this case B, is changing. Pearl also came up with something that's called the ladder of causation, for those of you who are not familiar with this. And he said there are 3 rungs on this ladder. First is association. So this is everything that we quantify statistically, purely statistically. That would be correlations, that would be dependence. By saying correlation, I mean linear correlation. So dependence would be more complex relationships between functions or objects. Then we have intervention. So this is what we have just discussed. So we tweak one element in the system, and we observe how other elements in the system are changing. And then we have counterfactuals. And counterfactuals would be like doing, in a sense, like doing an intervention, but in the imagined world. In Pearl's teaching, each of those ranks has a separate mathematical set of tools that allows us to talk about those ranks. Okay, so we will see that in association we can use purely statistical language. For interventions, we'll need something as do operator. Okay, and do operator means that we are changing something. Do operator can be expressed purely statistically sometimes, not always. And finally, for counterfactuals, we have another set of notation. An important aspect of Pearlian causality are directed as acyclic graphs. So these are graphs where you have nodes, you have directed edges. So there's always an arrow which signifies the direction of influence. And they are acyclic, which means that there are no direct cycles nor indirect cycles, which means that, let's say this is perceived gender, this is style, this is number of likes for a Reddit post maybe. So there is no path in this graph, there cannot be a path in this graph that goes from perceived gender to itself. It can be through other nodes or directly. If this condition is met, the graph is acyclic. And we will make use of those structures today. Okay, why model causality? How to increase the number of non-commercial space launches per year? So there are probably many answers to this question. One answer that is a data-driven answer is to increase the number of PhDs in sociology in the US. This answer comes from the first rung of the ladder of causation, so association. And it comes from this data that was collected by Tyler Virgen. That's one of the on the graphs of the graphs on his site, on his website. And as you can see, the correlation between those two, so non-commercial space launches and sociology doctorates in the US, are very strongly correlated. And this correlation is strong over more than a decade. So you can also see this. You can also see this as a scatter plot. Maybe that's less impressive, I don't know. And so this answer, most people would say that this answer, increasing the number of sociology doctorates in the US, is not causally related with space launches, right? Most of us would say so. Most likely there is a common cause to this. So maybe in those years, there was something happening in the global economy that was influencing both variables, or maybe some other mechanism. And now this leads us to an interesting conclusion. When we think about the state of contemporary of modern NLP, we can often hear people talking about models hallucinating. What does it mean that a model is hallucinating? Language model.
I mean, they're inventing stuff. Basically, if I ask them to write a function with a specific package, but the package is too new, they don't like, so the model doesn't know it, so it will just invent stuff that isn't there and obviously wrong.
Mm-hmm. So the model, so we will ask the model to do something, and the model will invent this on the fly. That's right? That's what you're saying? Yeah. Okay. But now, one thing is that we don't need large language models to experience hallucinations from a model, and linear regression will be enough for us. Which means that a very simple model that we can use, that many of us probably have used in the past, can actually give us results that are hallucinations. And this comes almost directly from the fact that we often mix the ladders, the rungs in the ladder of causation. So let's see why. Let's imagine a fire alarm system. And in our world, we will have just three variables: fire, smoke, and alarm. And the alarm will react to smoke, okay? So this is one class of fire alarms. I'm not an expert on this, but I checked it. One class of fire alarms that react to smoke particles. So they have smoke detectors, and they set off when the smoke is detected. Now, symbolically, we could express it this way. So we have fire that causes smoke, that causes alarm. The interesting fact about this is that fire and alarm are independent given smoke, which means that if there's smoke, the alarm will set off with some probability. If it's a probabilistic system, or if it's fully deterministic without errors, it will just set off. And it doesn't matter if there's fire, okay? So we can imagine a situation where we just open the window and there is fire outside, the smoke is coming inside, and the alarm starts. Now, this property is not a property of alarms only. We can generalize it, and it will work for any variables. So if you have a variable A causing B and B causing C, if we control for B, A and C will become independent, okay? Because the only dependence, or the only variability that C has in common with A goes through B. Do we have any questions here? No, okay. Now this structure is called a chain. It has its name. And now if we think about different structures that are possible with three variables, we'll get two more. So we have a fork where B causes A and C, And what will happen if we control for B? What would be the dependence/independence pattern here? So in the previous one, we said that if we control for B, A and C will become independent, but they are dependent if we are not controlling for B. So now we have the second pattern, which is called a fork. What will happen if we control for B? Will A and C become dependent or independent?
They should be independent, right?
They should be dependent if we control or if we don't control.
I mean, if we control for B, like if we create B, we should expect like some relationship happening, like
Mhm.
separate or something similar to both A and C.
So what you say? What's your name?
Michele.
Michele? Okay, so what Michele said that if we change something in B, then we should expect some differences in A and C. That's okay, but if we cannot intervene on the system, if we only can observe it. Now think about statistical control. We observe these three variables, okay? And now if we look at the correlation, let's say everything is linear, very simple. If we look at pairwise correlations, would A and C be dependent or independent without any interventions? Do we have any guesses here? Yes?
After controlling for B, they should be independent.
After controlling for B, they should be independent. And without controlling for B?
Well, it depends on the correlation coefficients. So like, if there's like positive correlations, there might be a scenario where they have like cancelling out correlations, but in most cases they would be dependent.
Theoretically, they could cancel out, yes, but that would be very rare. But probably in real world, highly unlikely. Yes, so this is a very good answer. So controlling for B, A and C will become independent, but if we are not controlling for B, we are just looking at pairwise correlations, they will be dependent, most likely, very likely. So now the independence pattern within chain and within fork is the same, right? So if we control for the middle variable, it renders the variables on the left and the right independent. Now the third structure is called a collider. What will happen if we control for B here? Okay, so collider is very special because with collider, the pattern is reversed. So we have two causes, A and C, that are causing B. And if you look at correlation, at the correlation coefficient between A and C, or any other measurement of or metric of dependence, A and C will be independent pairwise. But if you control for B, they will become conditionally dependent. Okay? You can think of it that controlling for B enables the flow of information through this variable. This is the least intuitive one, I would say, but it is very important in causality. So the difference between these behaviors between collider and both chain and a fork makes causal discovery possible. But it's also crucial in causal inference, because if we control for a wrong variable in our system, we can actually enable information flow in the system that is not real. Okay? And we'll see this in a second in the regression analysis. So what I did here, I took three variables, A, B, and C. I generated those variables according to those three patterns that we have seen. A chain, a fork, and a collider. And I ran an analysis of A predicting C, controlling for B. And as you can see, for chains, B is a significant predictor of C, but A is not. Okay? So if we haven't controlled for B, A would be a significant predictor for C. But if we control for it, A becomes independent. The same as you suggested, the same happens for a fork. B is a significant predictor of C, but A is not. But for collider, the pattern is different. Both are significant when we control for B. So to see this in practice, let's do some coding. So we'll need 5 steps for you to open the environment. You can do it in your computer, or we'll also do it on the screen, so you don't have to. So go to bit.ly/PyData Berlin 23. And this should open a GitHub repo. Then you need to copy the address of this GitHub repo. Something wrong here. Wow, that's so bad. I gosh, with. It might be case sensitive, yeah. Is it?
Yeah.
Okay, good. Thank you. So this is case sensitive. You need to say Pi with capital data, capital, and Berlin capital letters. Okay. Have it. Then you need to copy the link from the browser when the repository when you open the repository, and then go to collab research google.com, and then choose GitHub. There will be this window, and paste the link and click the search icon, and then it should open the GitHub link for you. Now I'm trying to, okay. Oh, that will be difficult, but I only see this here. Okay, does anyone need some help? No, okay. Okay, so you can run the first cell. It will install some stuff. Before you do it, you can you can make sure that you have GPU. Run anyway, cancel. GPU runtime. Is it here? Change run. Can you help me? Is it GPU now?
No. Yes.
This is GPU?
Yes.
Thank you. I'm not sure if I turn it off. Okay, so we can run this code. And we have some stuff, random seed and so on. And then we have data generating processes. Okay. So let's see if it's executed. It's still executing. Okay, so first we build a DAG like this. And DAG stands for directed acyclic graph. As we said, we have X causing Y, and we have W causing X and Y. So you can see that there's a structure here what is the structure between X, W, and Y? We have a collider, fork, a chain.
Fork.
This is a fork, yes, exactly. So it's a fork structure. So now, statistically speaking, X and Y, if we remove this path, and this is a fork, X and Y will be still related through this path, right? Because we said that in a fork, if we don't control for the middle variable, the variables on the ends will be related. So now if we run an analysis and we don't control for W, then our estimate of the influence of X on Y will be biased, because we will have this influence here on this path, the true path, but also there will be some influence going here. So we need to control for W in order to get an unbiased estimate. So let's generate some data according to this graph and run an analysis. Okay. So what we're doing here is we say that W is some random vector, okay? X is caused by W and some noise. And Y is 5 times X plus 2 times W plus some noise, okay? Then we run linear regression. This is Stats Models API. And we can look at the coefficients. And you will see that the coefficient for X is 4.99, so it's almost 5. The coefficient for W is 2.007 something, so it's almost 2. It's almost exactly, they're almost exactly the coefficients that we designed there. This also shows us that linear regression can be interpreted causally if certain assumptions are met. One of these assumptions is that there is no hidden confounding, which means there are no more variables like W that are causing both X and Y. If we are sure about this, linear regression can be interpreted causally. Okay, let's see the second data generating process. The second process is different. Now we have X and causing Y, and both X and Y are causing W as well. So what will be the structure between X, W, and Y? We had a chain, a collider, and a fork. Again?
Maybe a collider, because both are in the end are influencing W.
Yes, exactly. That would be a collider. That's a very good answer. So they are both causing W. Now, if in this analysis, because we said before, collider has the conditional independence structure that is reversed comparing to forks and chains. So now, if we control for W in this analysis, let's see what's happening. So first, X is some random noise, okay? Y is 5 times X plus some random noise, and W is 5 times X plus 2 times Y plus some random noise. So we expect that the coefficient for X will be 5, but it is -2. Oh, this is pretty far away. There's also some coefficient for W, which doesn't make sense because W has no influence on Y, right? But if we go to the rank 1 of the ladder of causation, which is association, it makes sense because they share some information. There is some variability in Y and X, in W and X, in W and Y that are shared. And it's shared because they are related. But the direction of this relationship, causally speaking, is reversed than what we see comparing to what we see here. So as you can see, our linear regression is hallucinating now, right? There's a strong positive influence of X on Y. The coefficient is 5, but the regression tells us that it's -2. Okay? Do we have any questions here or comments? Okay, those structures, do you feel this is clear? Yeah?
Just very general.
Yeah.
Y is always like your output here?
Yes.
Okay.
Yes. Yes. So X is the treatment and Y is the output. And W is some additional information.
All right.
Great. Any more questions? No. Okay. So it seems we have clarity regarding this. Good. So let's get back to the presentation. And let's talk about large language models. So where are we today with language models and causally speaking? This is one of the examples from my book in the chapter on counterfactuals. And it goes, John has coffee sensitivity. He drank coffee in the morning, and his stomach now hurts. Okay? And the question is, would his stomach still hurt if he had not drunk the coffee? So in the book, we have a formal treatment of this example. We have a set of equations, and we show how we can retrieve counterfactuals in certain cases purely analytically. But here, we just ask ChatGPT to answer this question for us. And so ChatGPT has, no, his stomach would not hurt if he had not drunk coffee, assuming that his coffee sensitivity is the only cause of his stomach ache. If John has a sensitivity to coffee, then drinking coffee can cause adverse reactions in his body, such as stomach pain. Therefore, it is likely that the coffee he drank in the morning is the cause of his current stomach ache. If he had not consumed the coffee, he would not have experienced this specific reaction. What are your thoughts about this?
Seems sort of correct, because it's also specified that if this is the only cause.
Mm-hmm.
So it seems like given the information in the prompt, this is the likeliest outcome based off the information that the model is available.
So you say that this seems to be correct, especially that the model also gives us this restriction that assuming that this is the only cause. I agree with that. I think this is a really impressive answer. And before ChatGPT, that would be, you could only hope for answers like this from large language models that we had previously. But, as they say, hope is not a strategy. This is one of very good answers, like very good causal analysis, very good causal answers that I got from ChatGPT when I was testing it early on for causal questions. I was very impressed by this. Here we have a tweet from Judea Pearl, who was also doing tests lately with GPT-4 and so on and so on. And he gave like a set of examples to the models. Some of the answers were correct, some of them were incorrect. But it seems that many people got very good answers, but this is not always the case. So now I gave the model the description of the graph that we've just seen, the one with a collider, and I asked to determine, and I asked if we should control for W. And the model said to determine whether we should control for W in the model that seeks to understand the impact of X on Y, we need first examine the relationship between X, Y, and W, and then it gives a long explanation, and it concludes, therefore, to understand the impact of X on W and isolate its effects, it's advisable to control for W in the model. And it says this is because the variation in Y that is explained by W is not due to X alone, but also to the noise and the contribution of Y. So this is an argument that seemingly sounds very reasonable, because it says there's some variation in Y that we can see in W, but we cannot see it in X. And so if we want to make our estimator, reduce the variance of our estimator, we should control for W. But the problem is that W also opens the path between X and Y, and as you have seen, it changes the coefficient essentially in an arbitrary way. So you can get effect where there is no effect, reverse sign, and so on and so on. So this argumentation is incorrect. And there are more examples like this. So there are essentially two papers from last 2 weeks. The first one comes from the Microsoft research team from Chongqing and the team that works on NLP and causality there. The second comes from Technische Universität Darmstadt, from Moritz Willig and Matej Zaczewicz and their team. And they both present similar conclusions, and they say that the large language models might give us good causal answers sometimes, but they do not understand causality by default. Moreover, the team from TU Darmstadt proposed a very interesting formalism where they say that the model is actually learning a meta-structural causal model strictly from language. So an interesting research was performed by Amit Sharma from Microsoft. He took a famous causal data set that is called Tübingen causal pairs. You have pairs of two variables. And this data set is often used to benchmark causal discovery algorithms. And he passed the questions about all those pairs to ChatGPT. And he got accuracy of 97%, I guess, if I remember correctly. And the best state-of-the-art algorithms go up to 83, maybe.
Do we know if it was actually trained with the information as well?
Yeah, so that's a very good question. So the question is if we know if it was trained on this information. So as they say here in this lengthy description, the model likely was trained on this information, right? So it had information about the connection of altitude and temperature, maybe it took it somewhere from Wikipedia or another source, and the same is most likely true for other pairs. And this is the conclusion that the researchers from Darmstadt make, that the model is learning a causal model of the world, but strictly from language, right? From statistical dependencies in language. And they formalize this mathematically in a pretty elegant way, and they call it a meta-SCM. They also say that they propose that those foundation models, those large language models, might be exploiting a loophole in the causal hierarchy by Pearl. So CHT, it stands for this ladder of causation and so on. And this is very, very closely related to another research by Michaela van der Schaar and her lab, where researchers proposed rank 1.5, which is between association and intervention. So sometimes we might have models that might give us a useful causal information, but without theoretical guarantees. And they have a very interesting matrix where they put static and time-sensitive models and so on and so on. So the conclusion of this is that although those large language models can be helpful regarding causality, we cannot get guarantees from them at this stage. And some of the proposals for the future work are to combine those models with implicit or explicit causal modules, where model can use a module like this to get computations about causal relationships and then translate them back to language and return the output.
When you say a module, do you mean something like the plugin, stuff like that? Like it outsources something like maybe a library which does that and like interacts with the library checks its reasoning, and then the model converts it back to textual. Like,
So the question is, what do we mean by modules? Is it about a library? Yes, exactly. So that's one of the solutions proposed by Zhongcheng and the team. They say that there might be a causal module, a library, some code that performs causal reasoning for us, and then the model translates it back to natural language and returns the output for us. Okay, so the large language models that we have today, they are not causal. by default. So what can we do with NLP and causality? There are basically two broad streams of research. The first one is about causality and real world. So that would be about questions about, does altitude cause changes in temperature, or the other way around? Does gender cause articles to be less cited or more cited, or perceived gender? Anything like this. So any relationship that we have in the real world. And the second stream is about causal influences within the model itself. So what would have happened if we changed this embedding? What would change if we rephrase the question, and so on and so on. So we will focus today on the first one, on the real world questions. And there are basically 4 scenarios in this category. The first one is text as outcome. An example of this could be that we perform an educational program and we want to check if this educational program influenced the readability of the text that participants are producing. Okay? So maybe people are writing essays, then we run a program, and we want to understand if this program has impacted the readability of those essays produced by the participants. The second scenario is text as confounder. Confounder, which means a common cause, something that can cause the treatment and cause the output, as in the first example that we've seen in the notebook today. And here we could say how perceived gender affects number of citations. So the example from the beginning. And I built a DAG here because this is not that intuitive. At least I did not find it that intuitive in the beginning. So here we have perceived gender. Here we have topic of the article. That can be operationalized as an abstract. So abstract has information about the topic, and we have a number of citations. And here we have gender, the true gender, not perceived gender. And then we know that gender might affect the distribution of topics, at least in today's society, and it also affects the perceived gender. And so this path, if we don't control for gender here, this path is open. So we could control for gender, or we could control for topic, and any of those nodes will close the confounding path here. And finally, we have, not finally, but almost finally, we have text as treatment. So maybe how the way we communicate influences someone's choices. For instance, you could think about a use case where we transcript psychotherapy sessions, and then we want to see how the ways that therapist is choosing to communicate translates to the outcomes of the client. And that's finally text as mediator. How does perceived gender affect number of likes mediated by writing style? Okay, so we have this direct effect here, and here we have also mediated effect. So if we are interested in so-called natural direct effect, so only this one arrow here, we should control for style. But style is hard to define, right? So we can take a model, build embeddings, and then maybe we can try to train or fine-tune these embeddings in a way that will emphasize the relevant parts of the text. Okay, so let's talk about an architecture that is called Causal BERT. This architecture has been introduced by Victor Veitch and colleagues in the article called Adapting Text Embeddings for Causal Inference. It's an article from 20 or 21. And the basic idea here is that we take a large language model. In the original work, it was BERT. In the implementation that we'll be using today, it will be Distilbert, so a slightly smaller architecture. Then we perform some modification on this model, okay? We'll talk about this in more detail in a second. And we want to predict 8, so-called. 8 stands for average treatment effect, and is defined as a difference between counterfactual outcomes. So counterfactuals, we talked about counterfactuals briefly in the beginning. 2 counterfactual outcomes, we say that we assume that we have a binary treatment. And so this is the expected value of the outcome under treatment and some other variables, relevant variables, minus the expected value of the outcome given no treatment and the same set of variables. This equation is for continuous variables, but for this can be also for, we can also say this is probability, or this is a distribution. This is a distribution. And do it for categorical or binary variables or anything else we want. Now, what's the problem with this? So we said we take the outcome under treatment and the outcome under no treatment. So what can be problematic here?
It's hard to estimate because you have either treatment or not treatment, but not both.
So the answer was it's hard to estimate because we either have treatment or we don't. And this is so-called the fundamental problem of causal inference, that we only observe in the real world, we only observe just one outcome. So either somebody took a pill or they did not. And as you said, it's hard to estimate because now we essentially need to think how to build this alternative world in a way that is still realistic. So how do they approach this? So they propose a model that builds 3 different artifacts. Document level embedding, which is just a regular embedding in within the language model. Then we have a mapping from the embedding to propensity score. What is a propensity score?
In the binary case, the likelihood that a treatment is assigned?
You said that this is the likelihood that the treatment is assigned in the binary case, yes? Yes, that's a good answer. So this is the probability, or sometimes likelihood, that that given a set of values for x, for our variables, the treatment is assigned to this particular unit. And then we have mappings from embedding to the outcome. So this model learns those 3 things. And it does so in a way that goes like this. So we have this Distilbert. Then we learn embeddings, like traditional. So this is MLM, stands for Masked Language Model. What is a Masked Language Model?
The idea is that it's an unsupervised, it's a pretext task for an unsupervised learning where we don't have labels, so we try to make up labels by just removing at random certain words from sequences or from sentences, and then we try to predict these words, so fill the gaps here.
Yeah, perfect. Thank you. Exactly. So masked language model is this objective that we use in training large language models, when in unsupervised manner we just remove or mask certain tokens, and then we are trying to predict those masked tokens given the context. And this is how we learn the embedding. And now we use this embedding to estimate the expected value of outcome given treatment, and the embedding the expected value of outcome given no treatment and the embedding, and finally the propensity score, as you mentioned, which is the probability that the treatment is assigned given the embedding. There are a number of assumptions for, for this model. For those of you familiar with causality, they won't be probably surprising. So first one is no hidden confounding, which means that we have this graph X, Y, and W causing both of them. We observe all the nodes W in W. Then we have positivity. What is positivity? Mm-hmm.
The positive probability of being treated.
Mm-hmm. It's the positive probability of being treated given a set of variables, that variables take a given set of values. Thank you. And finally, no leakage / consistency. Who knows what is consistency or no leakage? Mm-hmm.
There is no of the possible values in the control are present.
I cannot hear you. Can you say?
All the values possible in control are present in the treatment.
Okay, I could not hear you. I will go to you.
All the possible values in control
Mm-hmm.
are also present in the treatment data.
All possible values of control are also present in the treatment data set. That's positivity. That's a very good description of positivity, in other words. Consistency is slightly different. So it says consistency is a more complex thing, but let's focus on no leakage. This means that the treatment by one unit is not influencing the treatment for another unit. Okay, so if we say this is treatment for you, so you get the treatment, but if you did not get a treatment, you are not influenced by her treatment. Okay? Do we have any questions here regarding the assumptions? No. Okay. Okay, so let's do some coding. Let's go back to the notebook. Okay, and we will use the implementation from Reed Present from Microsoft, who implemented Causal BERT using PyTorch. The original implementation was in TensorFlow. I actually wanted to use TensorFlow 2 implementation, but I had some challenges with running it in Colab. So we'll run this PyTorch stuff. This is not available as a library, but as a repository. So you can say you can type Causal BERT PyTorch in Google, and you should find this repository. And then we will import the data. It's called test data, and it comes from Read Present as well. And as you can see, this data has 4 columns. So this is text, just a free text. Then we have treatment. We have confounder indicator, and we have outcome. And the outcome is binary, and this implementation only works for binary outcomes. Okay, so let's instantiate the model. This wrapper is like very high level, so we don't need to. So we don't need to do too much low-level coding. And as you can see, it's downloading the model from Hugging Face. And what's inside, you can see that it's Causal BERT from pre-trained, and Causal BERT, if you look into this class, we'll call DistilBERT, and then use pre-trained DistilBERT for training. Now we have a bunch of parameters here, so let's go through them. We have batch size, which is batch size. That's pretty self-explanatory. We have G weight, Q weight, and MLM weight. So those weights are weighting the cost function in the training. G is propensity score. This refers back to the original paper when they call propensity score G, which is not very intuitive maybe if you're familiar with the literature, but this is what they do. Q is the embedding. Q is the embedding under treatment. So I wanted to go back to the presentation. And I'm not sure if that will be easy. Okay. Okay. So G is this thing. We're trying to estimate the probability of treatment given the embedding. Then Q are those two things. So the probability or the expected value of outcome given treatment and given no treatment. And MLM, objective, this is the traditional objective for the embedding model. And now all three of them has their own loss components in the training, okay? So the influence of the embedding, you can decrease it, you can basically weight them. You can balance them, you can make the masked language model objective more important, less important, and so on. So the authors in the original paper, they conclude that that using masked language model is beneficial. They also compare it to other approaches like bag of words and so on. And so these are the default values proposed by Prisant in his repository. Now, if you want to use this in practice, my recommendation would be, if you can afford this, to split your data set into training and validation and try to find optimal values for those losses empirically. Okay. So now we can train the model. There is a train method in the causal BERT wrapper. We take texts, we take confounders, treatments, and outcomes, and we define the number of epochs we want to train for. Yes, of course.
If you open the data frame where we see one of the text examples,
Yes.
Could you explain what the exact task is?
Yes.
Because I read the text and then I'm not sure what is the
Yes.
model actually supposed to do.
Yes. So that's a great question. So while let's see if it's training, it's training. Okay, so that's a great question. The question is what exactly the task is. So this data, let's talk about this data for a second. So this data comes from Prisant, and I don't know its exact source. These texts are about music. So this might be comments from some subreddit or maybe another online forum. Now we have some treatment here, which is maybe in a similar data. So first of all, I'm guessing a little bit because this data set is not documented anywhere. I wanted to bring you another data set from like a real world problem, but unfortunately it was impossible. So that's why we're using this one. But now similar data sets, very similar data sets, usually are structured like this. So text is some text from maybe an online forum. Then the treatment is maybe if people have specified gender in their profile description. The outcome will be maybe a like or a lack of like, or I don't know, if somebody reposted this, anything like this, some action that people take. And then confounders here will mark the confounding content in the text. Okay? Does it answer your question?
So confounder, what is the confounder?
so confounder is something that that influences both the treatment and the outcome. Now, if we had this, so let me show you in the diagram. I think it will be easier.
The outcome in your example would be a like or something. Or would be
Yes, I think this is how we should interpret this particular data set. Yes. So some action. So for instance, yeah, so we have gender here. Then we have perceived gender that is coming from the, I don't know, your profile description or your icon. And there we have some outcomes, some user action. And then we have text. And maybe this text is influenced by gender as well, right? Because maybe people differ culturally, or I don't know, whatever, or biologically in some way that influences their choices of the topic. And then we can have maybe other confounders. Maybe there is something more in your profile that is also influencing your perceived gender and the user action. And then we can provide a categorical variable that will mark this type of confounder. Okay, maybe in this particular implementation, we can only provide categorical variables. So that will be like 1, 2, or 1, 2, 3, 4, 5, and so on, discrete values.
So what would it mark? Like what would 1 or 2 mean?
So this is arbitrary. It can be anything that you think is a confounder in your setting. Anything additional to the text.
Profile picture, maybe 1, and maybe like
maybe a profile picture, yeah. Maybe a profile picture, or maybe something else in your description. So if we had this example, X and Y, X causing Y, and then we had W. So W doesn't have to be just one variable. It can be a set of variables.
So we're not in the text as confounder scenario, but we're in a different one?
No, this is text as confounder, but there might be also different confounders. Okay? It might be like a broader set of confounders.
Okay.
Make sense? Not really?
Well,
So you can have like 2 variables that are causing the treatment and the outcome, for instance.
yeah, I get that. In abstract terms, it makes sense. I just wonder in applied settings, like.
So that could be a profile picture, for instance. I think this is a very good example. So you have text, but you also have a profile picture. So profile picture will influence your perceived gender because people will say like, hey, it's a girl on the picture, it's a guy on the picture. And there it can also influence the outcome because maybe people find you attractive, right? And they will be more likely to click a like under your comment or repost it. But the text of your comment also is also important.
I guess what I'm a bit confused about is that, like, I thought, like, finding or confirming these causal relationships is what we want to find out, but, like, deciding this particular thing is like a confounder is already kind of assuming the thing you're investigating.
So that's a very good point. Now, in causality, we usually talk about 2 broad categories of tasks. So one is causal discovery, which is about discovering, hopefully, as automatically as possible, causal relationships between variables. And then we have causal inference, which is just quantifying those. So everything we talk about today here is about causal inference. So we had this idea, one of the assumptions was no hidden confounding, right? This might be a difficult assumption, but if you assume that you know all the confounding variables, well, these methods will be helpful for you. If you say, like, I have no idea, maybe there's like 500 other confounders, then the results of this will be highly risky to use them in practice. Does it answer your question?
Yeah.
Yeah?
You got a question online?
Yeah.
So in reality, we are going to have a lot of confounders. So should we have to include all of them in the model?
Mm-hmm. So the question online was, in reality, we'll have a lot of confounders, so should we include all of them in the model? That's a very good question. Often, we are not able to exclude all the confounders. If we want those methods to work and have all the guarantees that they might have, some of them have more, some of them have less, then we should include all confounders in the model. Now, from my practice in the industry, I can tell you that usually the process looks like this, that you start with some model with your best expert knowledge that you can gather all over the place. Then you build a model. Then you generate some data from this model, some predictions from this model. And then you compare this to some new data. And then you iterate and you improve the model. So this is usually the process that I see in the industry and I also recommend. Because in many cases, especially when we talk about like open-ended complex systems, like, I don't know, social media, whatever social topics, and so on, it will be very, very hard to control for all confounders. Now, another way to work with those methods is to run experiments. So if you are able to run an experiment will basically cut, where is the treatment here? So the experiment, you can think about running an experiment as cutting off all the arrows that are coming into the treatment in the graph. So you are removing this arrow by running an experiment. And by experiment, I mean randomly assigning perceived gender, in this case, your treatment. And now your data is unconfounded if you run an experiment. So hopefully that answers the question. Do we have any more?
Right now, not yet.
Not yet. Okay, good. Okay, let's get back to the model and see. And see if it has trained. Okay, it's finishing. So put 2 epochs here. It might not be enough, or it might be enough. Okay, so the training has concluded. So now we can take the model, and it has a method called ATE, average treatment effect. We pass the confounders and text, and this will return the average treatment effect for our data set. Right? So we are doing an inference task, not a prediction task. We are checking the average treatment effect on the same data set.
You got another question?
Mm-hmm.
So you mentioned that the 4 scenarios are text as outcome, text as confounder, etc. All these 4 scenarios, and what is this?
So this is text as confounder as well. This is text as confounder, and this method can be also used for text as mediator. But as far as I understand this particular implementation, it only works for text as confounder.
Could you give an example again, once again, for text as confounder?
Text as confounder?
Or if I think of your diagram, I wonder, would the name of the author be the text that is confounding, or?
No, that will be, just let me, okay. So now, text is an abstract of, I don't know, abstract of a paper, okay? And there is this path between gender and abstract that opens the path between perceived gender and a number of citations.
Yeah.
So if we control for topic, we'll close this path. And now only this path remains, which means that we now have the effect of perceived gender of numbers of citations. But if we don't control for this and we don't control for this, and I assume that the real gender is unobserved here, then this path is open. And this will change the estimate for this effect here. So anytime you can think of text influencing like your treatment and outcome, this will be text as confounder.
Why my treatment?
Yeah, why your treatment?
Why would it influence my treatment?
Well, it depends what your treatment is. Like anytime it happens, it will be a confounder. Now, of course, it depends on what your treatment is, but it might affect your treatment. I'll try to think about another example when this is happening, and we'll try to give it to you. If not now, we can try to talk after the talk. Yes?
I don't know, I find it a bit confusing. I think the terminology of treatment, like, it doesn't mean that you intervene to change it. It just means that it's just an observed variable. Maybe that's the thing.
Yeah.
It's difficult to give. I don't know, I find it.
Yeah, that's a very good comment. So the comment was for the people online that the treatment doesn't have to be, I don't know, a drug or something that can be just one of the observed variables, that you are interested in the effect of this observed variable on another observed variable. So there's a strong connotation about the treatment being something that we manipulate or like something hard and so on. So this might be useful for some people. Thank you. That's a very good comment. Okay. And so we have it, and the average treatment effect here is minus 0.22. The thing is that, and this is pretty. The thing is that this is pretty stable. I ran this model like, I don't know, like a dozen of times, and it was always very similar to this. So maybe minus 25, minus 24, minus 22, which is a very good sign. Okay, so let's get back to the presentation. Okay, so a couple of conclusions from the paper. Language modeling helps, which means that the authors have tried also using different approaches. If I remember correctly, they're using bag of words and this other stuff, and some other stuff, I'm sorry. And language modeling in terms of using large language models helps, in particular when we adapt those embeddings to learn this more complex objective function that models counterfactual outcomes and the propensity score. Also, another thing is that custom pre-training helps. So they notice that not only, let's take a step back. What happens when we train this model? We are in so-called fine-tuning regime, which means that we're taking pre-trained embeddings, and then we are learning our objective function starting from those pre-training embeddings. What the authors suggested here is that before we do that, a good thing to do is to take your data and run a couple of runs of unsupervised pre-training using this data. And they notice that this also improves the estimates.
Like in the normal regimen for LLMs? So
Again?
Like to run the unsupervised as normal LLMs do? Like
Yes.
Just to predict the next token, blah, blah, blah.
Yes, exactly. So the question was, should we do it in the same way as if we would train a large language model from scratch using this masked language model objective? And the answer is yes. So that's exactly what they say. You start with the pre-trained model, but you still run just the masked language objective for a couple of runs using your data set, and then you do fine-tuning using the method with the complex loss function that we've seen in action today.
Do they explain why? Because,
Do they explain why?
Yes. My intuition would be that it is necessary to give the model information on what you are writing, like what you're the actual language, what is being used, like the text.
So the question is,
After you have the text like in the memory of the language of the LLMs, then you ask it how does like the inference work, like causality, stuff like that. First
so
you have to have the information.
yeah. So the question is why this is the case. So I think this is something that is that we often see in the industry, that when you adapt a model to a new task, for instance, I used to work at Ironscale, which is a cybersecurity company, and we're training large language models on to predict certain qualities of emails. Okay, now you can imagine that email language might be slightly different than general language on the internet. The distribution of emails might be slightly different than the distribution of overall language on the internet. And then not only fine-tuning this model for our classification task, but also training this on this email language in particular before we train the model on a task might be beneficial, because it makes the distribution that the model learns more similar to your domain distribution. Does it answer your question?
Yes.
Yeah? Perfect.
Have you ever heard of the theory and interpretation of LLMs models as simulators?
Again?
Like, have you perhaps maybe read about the theory or interpretation that LLMs are actually simulators underneath the hood?
So the question is about the theory that LLMs are simulators. No, I haven't read a paper like this, but I can imagine that you could probably say this about any generative model to an extent.
Yes, the idea would be that like this step works because the actual, in order to predict correctly the next token, you have to have like the better the word model you have, the better your token prediction. So eventually you are able like to predict personas. We say like, you know, when you break the model and they start like going on a ramble, stuff like that. But also probably the same reason why you need the step before, because like actually now the model has like enough information to simulate like what's the actually next the language to the mails, and then we apply the causal inference and probably that's why it really helps.
So the comment was that if we think about large language models as simulators, the better representation of language we learn, the better outcome we can expect, and we can also learn more specific things like personas, you said, right? And so on and so on. And this is likely related also to the observation that the authors had here. Okay, so we conclude here. And if you want to learn more about causal inference and natural language processing, this is a great paper by Amit Feder from Technion in Haifa, and his colleagues from like all over the place, as you can see. And this is a great overview of work on the intersection of causality and NLP. I also have a QR code for you here, so you can make it. You can just make it like this. Yeah.
Before we conclude, I think you have quite several online questions.
Okay, we have more questions. Good.
So, how often do you test for different but valid DAG configurations that explains the observed data?
Once again, how often?
How often do you test the different DAG configurations?
The different what?
DAG configurations.
DAG configurations, DAG configurations that explain the observed data. That's okay. So the question is how often we test for the structure of DAG. So DAG is the directed acyclic graph. That's a very general question. So in the sense, it's hard to answer. But it's good to test for this, right? Maybe let me take a step back. There are different use cases. So far we are talking about like social models that are trying to model some social phenomena. And these are often open-ended and complex systems. And in this sense, it's very difficult, or might be very difficult, to exclude all the hidden confounding or control for all the hidden confounding. But not all systems are like this. So for instance, there are very successful implementations of causal models in the industry where you have for instance, systems like production lines that are virtually almost closed. And so the influences from the outside are very limited. And often those systems also are well documented when it comes to how information in those systems flow. So this might be very, very different case. But if I had to give you like a general answer, well, I would test to the extent where I feel this model makes sense and fits the data well. I know it's broad, but I guess that's the best what I can give in a general sense.
Okay, I guess there are more specific questions here. So there are some studies stating that propensity score perform poorly to decrease the imbalance between control and test. Do you also use alternatives such as Mahalanobis?
Mm-hmm. So it says that there are studies that show that propensity score can perform poorly. I'm not sure which studies the person asking the question is referring to. There are certainly studies that showing that propensity scores are a very bad choice when it comes to matching. So matching is another type of an estimator that can be used in causality, but matching on propensity scores can lead to very detrimental results. So this should not be done. In other cases, I don't know. Perhaps there are studies that also show some problems with propensity scores in a broader sense, but I'm not aware of those. Here in this work, people usually work with propensity scores, if anything.
Okay, good. And I guess you have one last question.
Yeah. Mm-hmm.
So in the case of text as outcome or treatment scenarios, how would you quantify the ATE since the text is not a numerical variable?
Mm-hmm. That's a great question. So the question is, in case of text as treatment or outcome, how would you quantify ATE given that text is not a numerical variable? So in general, we've seen the formula for ATE that is for binary variables. And in our case, the outcome was also binary, but it doesn't have to be the case. So we can have continuous treatments and continuous outcomes as well. That's the first thing. The second thing is that if we treat text as outcome, we might sometimes just say, hey, if there was some feature in the text, right? So maybe if certain set of features in our embedding space has certain values, then we just say, okay, this is 1. Otherwise, it's 0. So it can be binarized sometimes. And also, it can be a continuous variable. When it comes to the treatment, it can also be a continuous variable. Moreover, it can be a multivariate variable, or multidimensional variable. So we can have an embedding space, perhaps cast down to some lower dimensional space. Like, I don't know, maybe we have 8 dimensions, and these 8 dimensions, continuous 8 dimensions, define our treatment. And this is also possible, and this can be done. So there are models that can take multiple or multidimensional continuous treatments. And this could be also generalized to natural language, although I don't know papers like this, I think, at this stage.
And you got requests about, like, could you send the slides and some papers to the Discord channel, for example, in this A586 room?
Mm-hmm. For how long will the Discord be open?
I'm not sure. I think it stay open.
Okay, so if it stays open, I will do it later today. Otherwise, I will add some more papers. So there's one paper, but I will add more papers to the repository that we used for the talk. Okay?
Yeah. And I don't see anything coming, so
okay.
That's it. So as an outcome, you will get a loud applause for the ending.
Great, thank you so much.